Good morning, students. Welcome to the mass transfer course. Today will be lecture 18. Here we are discussing about the interphase mass transfer. And in interphase mass transfer, we are discussing about the material balance in mass transfer equipment, and through the material balance we will get the operating line. We know the equilibrium relations between two phases for a particular solute. Now we are trying to get what is the operating line, in which concentration the process is getting operated. Okay, so that we are interested in this chapter, and we divided this thing into four parts. The first one was steady state counter current mass transfer, and in previous lecture we have discussed this thing in detail. Here for steady state counter current process, we have seen how to construct the operating line, and if we during construction of operating line, if we consider LSGS and capital X capital Y, that's mean mole ratio, then our slope of operating line will be LS by GS, and which is constant because LS and GS are the solute free flow rates or inert flow rates. And we have seen if we make the calculation in terms of mole fraction, small x, small y, LS, L and G, total molar flow rate L and G, then the slope will be L by G, but L and G will change along the separator, so that slope will change, and therefore that curve will be non-linear. That's why there is an advantage in calculation of operating line considering in terms of mole ratio. Few days back, one student asked me one question, sir, mole fraction is there, why we need the mole ratio? And that time I told you, now you learn this one, later I will justify why you require, what is the advantage of mole ratio concept. If you go in mole ratio concept, then LSGS, that will be solute free basis, and therefore in calculation slope of operating line, construction of slope of operating line will be easy because it is constant. But if you take the mole fraction, that concentration dimension unit, then it will be L and G, and LG will continuously change, and therefore slope will change. Now I think you understand what is the advantage of using capital X, capital Y, okay, mole ratio concept in calculation of our operating line. Today we will discuss two more things, that is second one, steady state co-current mass transfer and steady state cross current mass transfer. So in previous lecture we have done the first one, steady state counter current mass transfer. Today we will look another two, that is steady state co-current mass transfer and steady state cross current mass transfer. Now if you take the steady state co-current mass transfer, the equipment is same, okay, and we took the nomenclature, bottom is 1 and top is 2. Okay. Now as the co-current means both the lighter phase and heavier phase will enter in the from the same direction and will go out from the same direction. That's why if you see here G phase, the one that is G1 Y1, okay, then corresponding mole ratio Gs capital Y1, and liquid also entering from the in the same direction. G phase and L phase both are entering in the same direction. If you take the mole fraction, then X1 L1, and in terms of mole ratio calculation, Ls capital X1. Now let's take, if I take the same example, absorption of ammonia from gas phase to water. Okay, so if you take this water one phase and air, 10% ammonia is in air, so it is entering, and if in outgoing, if complete removal, then y2 will be 0. Okay, now the ammonia will move from gas phase to liquid phase. Therefore, that concentration of ammonia in liquid phase will increase gradually. Okay, so this will be your X2. So in this case, capital Y1 will be higher, capital Y2 will be lower if solute is transferring from gas phase to G phase to L phase. Okay, and in this case, then this will be lower and this will be higher, because here whatever the concentration of ammonia, it is almost 0 if you take the pure water, then 10 mole transfer from gas phase, so this there will be some value. So thing is that this is higher, this is lower, but here this is lower, this is higher. It is very simple concept. From material balance you understand this. Now what we do, we will do the similar way what we did in counter current. So we have taken two envelope. One envelope is this is envelope 1, so this is the extreme, and in between at any point, that is G is Y, G is capital Y, L X, capital Ls, and capital X. So nomenclature is same as your cocurrent. Okay. Now if you take the material balance for envelope 1, envelope 1 means up to this. So what are the entering? These two are entering. Okay, so GSY entering and LS capital X is entering, and outgoing is GSY2 plus LSX2. And now if you take this minus this GS, then you have to keep the same. Okay, so if it is Y, then you have to keep X, so then it is come to the negative sign. Okay, Ls X minus X2, so Y2 minus, if you take this negative side both, Y2 minus Y, X2 minus X equal to minus Ls by Gs. So here the slope is same, Ls by Gs, but with a negative sign. But in case of counter current, thus their negative sign was not there. That means slope will be constant but with negative. And if you take the, similarly, if you take the envelope 2, means 2 extreme, this one, okay, entry and exit, then instead of Y X, it will be Y1 X1. So that this will be the equation from material balance. Now if you take this one, Y1 is higher, X1 is lower. Here Y2 is lower, X2 is higher. Okay, so if you take this one, so if you take this point, so Y1 is higher and X1 is lower, and if it come to the this point 2, okay, this is point 2, so this is 1.1 and this is point. Whatever this is your, you understand, this is your y1, y2, this is low, y1 is high, but here x2 is high and x1 is low. And here the transfer is happening from G phase to L phase. And if you this point M, if you take any point in between M, that is x and y, this value, okay. So if you take from this point, if you take this one parallel to this, and corresponding this will be your the driving force for liquid side, and if you take the vertical, this one up to slope, and this will be the driving force for the gas side. But if you take here, then this will be that driving force and for gas side, and this will be driving force for that. That's mean here if you see, when you are coming from point 1 to point 2, your driving force is constantly changing. And if you take this, and if you take minus kx ky, that slope, then you will get for a particular point, okay, what is that if you get that interfacial point for this one, if you take this point and if you take minus kx ky, that is be xi yi, that will be your that interfacial concentration. So from 1 to from 2, so I came here. Now if I increase this, let's take, if I increase the height of this column, this, if it is goes, then this line will come here down. How much it will come? It will come up to this. When it will reach here, that's mean it reaches the equilibrium. If you increase the height of this column, then gradually it will come to here, this one. But after that, if you increase this height of this column, no, because it has reached the equilibrium, then thereafter no mass transfer will take place, and the corresponding that exit concentration will be this. These are x and y. You cannot go, you cannot make y that concentration in G, because it will that mass, because when it will reach here, there is no driving force, zero driving force, so no, after that no mass transfer. Thereafter, if you increase this the column, height of the column, then it will not be. So this is my operating line, and this is my upper equilibrium line, and mass transfer happening from G phase to L phase. Now if you take the L phase to G phase, R to S, the slope will be same, minus LSGS, okay, L phase to G phase, but it will be below this equilibrium, and this will be your operating line. And if you keep increasing the height, once it will reach here, then that means it reaches to the equilibrium. Okay, so in this case, this is the operating line for mass transfer from L phase to G phase. Now if you take the cross current, generally cross current mass transfer widely used in liquid equilibrium. Let's take, you want to extract BTX. BTX means benzene toluene xylene from petroleum cut. Generally in petroleum cut, BTX is there, benzene toluene xylene is there, but petroleum sale price is, let's take 80 rupees per liter, but BTX has a sale price 200 rupees per liter. So what I want to remove this one, instead of giving with selling, if I sell it with petrol, then price is low. So people they remove that B2X part from this petroleum, this uh, naphtha, from naphtha or petrol. So for that they use one chemical N-methylene pyrrolate. So this chemical generally what it will selectively remove this BTX from this petroleum. Both are, you remember, both are in organic phase. One is petrol, another is N-methyl pyrrolate, but these are not miscible to each other. Okay. But what is here? What is the concept? Let's take one phase, that is petrol phase. Okay, so petrol phase is there, the flow rate is there. This is, let's take cross current number one unit. Number one unit, I'm telling. Now what I will put the petrol, which has some BTX, the concentration corresponding. This is 1. Okay, that previous is 0. We assume, that's why I put this is 0 nomenclature. So GS, I kept it GS because it will not change, but capital Y0, small y0 and G0 it will keep changing. We know this one. Now this is the petrol with BTX concentration. Now I am using N-methylene pyrrolidine. Okay, for this one the flow rate is 1, but 0 means that concentration. Okay, or I can make it LS1. Okay, the flow rate I can keep what is the flow rate, but concentration is X0 and capital X0, small x0. Generally N-methyl pyrrolidine I am pumping from a particular, there is a container, okay, storage tank. From there I am pumping this one. So I am putting what that concentration, whatever the concentration, generally it is 0. Okay, and some flow rate I have given LS that 1. Okay. Now if you give LS1 and L10, what is the thing? Then what will happen? This unit actually is a combination of mixture settlers. Mixture settler. First I will mix these two. Okay. And thereafter I will allow it to settle. When we will mix it, then what will happen? When mixing, then petrol and N-methyl pyrrolidine will mix up. Okay. No, there will be dispersed phase. But then if we allow for some time, then N-methylene pyrrolidine and petrol will be in 2 phases. And that BTX will move from petrol phase to N-methylene pyrrolidine. Okay. So mixture and settler. So then if it is top phase is, let's take petrol, bottom phase N-methyl pyrrolidine. So with this point I can separate this thing. Okay. So mixture and separator, two combination of this thing, it is called generally 1 unit. So after first extraction process, okay, so then what will happen? LS N-methyl pyrrolidine, if it is same, it will come because it is inert flow rate, and X0 some BTX will come here. So that corresponds. And if you take the mole fraction, so what is L10? Some flow rate will change 1 and corresponding X1. Now whatever remaining petrol is coming from this, that one unit number 1, that has a inert flow rate GS, but that flow rate will be like this, G1 and Y1 and capital Y1. Okay. So now what I will do means y1 is some btx is there. Now I will put in a generally there will be one tank n methyl propane. Here I will set one pump. Okay, I have a pipeline, and everywhere there is a one valve. Okay, one valve will be there. So whatever I will open the valve accordingly the flow rate will. So this is a concept. So here whatever the flow rate, I can keep here different flow rate L20. Okay, but concentration what will be small x0 or capital X0, it will be constant flow. Here also will be same, here also will be same. But flow rate I can, whatever the opening accordingly, whatever my need, I can change this one. Okay, so let's take this LT0 and for second unit that is LS, but for second unit I can keep the flow rate different. Okay, so that's why LS2 and whatever this same thing here. So second extraction process corresponding the remaining BTX, because once it will reach to the equilibrium, that's mean it has reached here. Okay, welcome. We will see here also it has come here. So I cannot go further. So second I will do, I will come to the second unit, whatever the remaining. Okay, so I will put some N-methylene pyrrolidine, then another extraction, then corresponding the output will be X2L22. This will not change, this will be constant, same. Okay, and X2. Then in third phase, okay, if I take this one, so again I will put this one. So then whatever the is, if you take these three phases, that is then 3 units. So then it is remaining part, it is coming, that will be very less. So this is cross current. Okay, G phase is moving from north to south and L phase is moving from east to west. Now if you take this material balance, let's take for 1. So GS, what is entering? GS into this minus this. This is GS change equal to LS equal to x1 minus x0. So if you take y0 minus 1 x0 minus equal to minus LS, isn't it? So if you see this equation is similar to your co-current. Co-current means if you see this. So this slope will be like this, and after mixing, then if you take the settler, if you allow up to the equilibrium, once it will reach here, then nothing will happen. Okay. So if you take this one, let's take I have a Y0, that is high benzene content. Then if you take L0, okay, P1 first unit, okay, X0 and Y0, and slope is negative. So mixers, if you reach the equilibrium, the slope will be LS1 by GS. So you reach here first. If you allow it up to the equilibrium, generally it will be like, if you mix it, then if you take it slated, then it will reach to the equilibrium. So, and that is the exit concentration of X1, capital X1 and Y1. Now I am putting Y1 is there unit. Now again I am putting the X0, that unit, the X0 means this, so this will be 0.2. So again I will take this slope, that minus LS2 by GS, so it is coming to Q2 second. So again it is coming to that y2. Okay, so if you take another one, so then it will be y3. So in this way you can, with number of stages, you can bring this concentration from y0 to 1, but in a single stage you can come up to this once this flow is full, but I cannot come beyond below this because it has reached to the equilibrium. And this is for operating line for 1, this is for operating line for 2, and this is the operating line for 3. So this is the cross current, isn't it? This is the very easy and equilibrium. Keep it in mind, when we are operating line we are getting from the material balance, equilibrium line we will get from the thermodynamics, and for any system it will be known to. It has to be known, otherwise you cannot do them, because equilibrium will tell you how much, up to what extent mass transfer is possible. When will you reach there, after that you cannot make the mass transfer. So when that's why always when we are dealing with the mass transfer, always the thermodynamics is must, because from thermodynamics we are getting the equilibrium. So today we have studied the two more things. One is co-current, another is cross current process. Okay, and for that one we have seen that the slope of the operating line is negative, and it will it will touch, it is easy, it will come when you keep the height of the column high, then it will reach to the equilibrium. Thank you for your attention. Bye.